In this session, we will introduce several applications of homomorphic and septual analysis methods in speech signal processing. As to the convolutional homomorphic system, there are three subsystems to be designed. The first one is convolutional characteristic system, which convert the operation of convolution to additive. The general form of the characteristic system is complex septrum analysis. The second system is linear system, which is a kind of linear filtering to enhance or separate out one part of the signal, while weakening or removing another part. The third system is inverse system of the convolutional characteristic system, which convert the operation of additive back to convolution. In the application of speech processing, the deconvolution capability of the homomorphic system is often used. The following sliders will briefly introduce several examples of convolutional homomorphic system applications. Convolutional homomorphic systems are used for digital signal processing and deconvolution to recover useful signal. One of its important applications is to separate the channel impulse response and glottal excitation signal in digital speech signal processing. By use of homomorphic filtering or septual analysis, we could separate out UN or HN from the combined signal easily. The figure shows short-time homomorphic analysis of voiced and unvoiced speech. In the flowchart, position A is the input speech segment, normalized and weighted by a Hamming window. Position D is the septrum. Position C is the log magnitude of the original spectrum. Position E is log magnitude of the smoothing spectrum after homomorphic filtering. For voiced speech, the septrum plot D has obvious peaks, and the homomorphic spectrum plot E shows obvious format features. For unvoiced speech, the results behave oppositely. In general, the object of a deconvolution is to find solution of a convolution equation. When recording speech in reverberation environment, the restoration of speech that has been degraded through addition of multiple echoes. Usually, XN is the recorded signal, and SN is the useful signal that we wish to recover, but has been added with several echo signals. In another form, the speech SN is convolved with transfer function HN before we record it. The function HN just represents the reverberation characteristics that was applied to a physical system. If we know HN, or at least know the form of HN, then we can perform deterministic deconvolution. However, if we do not know HN in advance, then we need to estimate it. This is most often done using methods of statistical estimation. By use of homomorphic analysis, we could design a comb filter to remove reverberation and get the useful signal. Septual analysis also provides a way for the pitch estimation. The septrum of voiced speech intervals has strong peak corresponding to the pitch period. Septrum pitch detection algorithm has some advantages over autocorrelation-based pitch detection. It is assumed that the sequence of voiced speech Sn can be presented as the convolution of En, which is a source excitation sequence, and Hn, which is the vocal tract discrete impulse response. In the autocorrelation function, the effects of the sound source and the vocal tract are convolved with each other. This results in broader peaks and, in some cases, multiple peaks in the autocorrelation function. In frequency domain, convolution relationship between sound source and the vocal tract effects become a multiplicative relationship. The multiplicative relationship between source and the tract effects in substrum is transformed into an additive relationship. The effects of the vocal source and the vocal tract are nearly independent or easily identifiable and separable. It is possible to separate the part of the substrum which represents source signal and find the true pitch period. That is why, in general, substrum pitch determination is more accurate than autocorrelation method. For pitch detection, real part of the substrum is sufficient. The real substrum of the discrete signal Sn is defined as Cm, where Sk is logarithmic magnitude spectrum of Sn. The substrum consists of peak occurring at a high frequency equal to the pitch period and low frequency information corresponding to the format structure in the log spectrum. To obtain an estimation of the fundamental frequency from the substrum, we look for a harmonic peak in the frequency region corresponding to typical speech fundamental frequencies. As can be seen from comparing the speech segment to its substrum, this fundamental frequency is also the pitch period, of the time waveform. The search for such peaks in the substrum was the basic for pitch detection algorithm. Substrum method can be used for unvoiced and voiced detection. When the glottal excitation source is voiced, its complex substrum is not zero only at points that are multiples of the pitch period, and zero at other points. The distance between the first non-zero point of the complex substrum sequence and the origin point is exactly the pitch period. In the case of unvoiced sound, the complex substrum has no obvious peaks. By use of this feature, unvoiced and voiced sound can be detected. Substrum method can be used for extracting format features. The first step is to filter the substrum and take out the low time part. Inverse system processing is performed on the low time part to obtain a smoothing logarithmic spectrum function. The logarithmic spectral function contains format structure of speech. We can detect the peak values and estimate the frequency and intensity of several resonance peaks. From a view of homomorphic filtering, liftering is used to actually separate the vocal tract filter response from the periodical excitation spectrum. By applying a low-pass lifter to the substrum to extract the low-frequency components below the first harmonic peak, the slowly varying curve in red line results. The low-frequency components thus correspond to the resonance structure of the vocal tract. The final homomorphic spectrum peak corresponds to 4-minute frequency. Homomorphic system can also be used to design vocoder. A block diagram of the homomorphic analysis and synthesis system is shown in the figure. The spectral envelope information contained in the low time portion of the spectrum is updated and transmitted every frame. The excitation parameters are obtained by spectral pitch detection. The homomorphic filtering procedure combined with analysis by synthesis excitation coding is promising alternative to linear predictive coding LPC for low bitrate vocoding. That's all for this chapter. See you next chapter.